All right. Welcome everybody to the IEEE Get Blockchain Forum. This is the final day, Friday. This is tutorial session number 3, distributed ledger technology on directed acyclic graphs. And our first presenter is Sergey Gribniak from Waterfall, our signature sponsor. Sergey, go right ahead. You should share your screen.
Yeah, thank you. I start sharing my screen. So yeah, hello everyone. I welcome you here to our tutorial, distributed ledger technology based on directed acyclic graphs. My name is Sergey Gribniak. I'm the co-chair of IEEE Ukraine Blockchain Group. I'm also a PhD candidate at Odessa State Polytechnic University. My research topic relates to various applications of graph theory in distributed ledger technologies with a special focus on directed acyclic graphs. This tutorial consists of the following parts. We will start with an introduction to the graph theory. Sorry, do you see my screen? No.
Not yet. You need to share your screen.
Yeah, sorry, I was thinking that I'm sharing. Yeah. So, yes.
It's coming up now. Yes, we see that.
1 second.
And you want to go into presentation mode?
Yeah. Actually, that's a little slower. So,
great.
Yeah, now we, yeah. So, we will start from with an introduction to a graph theory. We will provide a definition of a DAG, and we will go through different types of DAGs applied in distributed ledger technologies, in short, DLTs. We will also briefly review a few other applications of graph theory in DLT. Then we will have a presentation from Lyman Baird about Hedera hash graph. His presentation will be followed by Damian Strajak from Aleph Zero. Then William Sanders will present IOTA, and after that I will present Waterfall, and the final will be the presentation by Juan Guillem about Phantom. Each presentation will be followed by a Q&A session. So let's start. Currently, we can find a number of different headlines on the internet, such as the one you see on the screen. There used to be not much clarity on DAGs, and some articles were even conflicting with each other. The state of distributed ledger technology research coverage improved quite significantly over the years. We can observe the improvement in the DAG-based direction as well. There were already multiple attempts to classify existing DAG-based protocols, and we will try to provide insight on this topic without going too techy for it to be easy to understand both for technical and non-technical audience. So a graph is a mathematical structure made up of vertices, also called nodes or points, and called nodes or points that are connected by edges, and also called links or lines. When the edges don't have a direction, the structure is called an undirected graph. An example of a graph could be a LAN network. Vertices are network routers, and edges are connections between them. This is also an example of undirected graph. In such graphs, degree defines the number of edges meeting in the vertex. If the degree of vertex equals 1, then it is called a pendant vertex. If the degree of vertex equals 0, then this vertex is called an isolated vertex. An example of such a graph could be the group of islands connected by the bridges. Islands are vertices, and in that case, bridges are edges. If the edge connects the vertex to itself, it is called a loop. If there are multiple edges connecting two vertices, they are called parallel edges. When a graph doesn't have directed edges as well as parallel edges and doesn't have loops, this type of object may be called precisely an undirected simple graph. An example of loops and parallel edges could be car roads. Connected base stations could serve as an example of a simple graph. Now we can discuss the directed graphs. When the graph edges have directions, the structure is called a directed graph. Sometimes directed edges could form a cycle. The example of the cycle is shown on the screen. An example of a directed graph could be a connection between one-way roads. If the roads are two-sided, that could be represented as an undirected graph or a directed graph with parallel edges. A directed acyclic graph is a directed graph in which edges doesn't form cycles. This data structure is widely utilized nowadays. Examples of the structure of folders, for example, example could be a structure of folders in the file system. They are also used in logistics. Directed graphs, they have actually two types of vertices. The first type is actually two types of degrees of vertices. The sum of all incoming edges is called in degree. The sum of all outgoing edges is called out degree. A tree is a special type of graph in which in this graph, every two vertices are connected exactly by one path or edge. If the edges have directions, the data structure is called a directed tree or a polytree. Bitcoin could also be represented as a DAG, in particular as a directed tree or a polytree. Vertices are blocks and their parent-child references are edges. In most cases, the block has only one predecessor and one descendant. When the fork happens, one block can have more than one descendant. Bitcoin utilizes so-called longest chain rule, where eventually the longest sub-branch of the tree is getting selected and keeps on adding the blocks, and the short one is getting ignored with all its blocks and transactions. Now let's talk a little bit about why we don't see Bitcoin or other blockchain projects being widely adopted for the whole society or any part of it. Among them are needs for standard, usability, and trust issues, regulatory compliance, clarity, and other issues. I would like to put additional attention to scalability. So on the screen, you can see the numbers of the most popular retail payment providers. To get to the level of mass adoption, distributed ledger technologies must achieve a comparable level of throughput. Blockchains are having typically less than that. There are multiple ways to address the scalability issue. Among them are payment channels, sharding techniques, layer 2 solutions, and sidechains. We will not go into the details about these techniques and discuss DAG-based protocols in more detail. There is a growing number of protocols implementing DAG-based techniques. There were multiple attempts to classify them, and the most intuitive approach is to answer the questions of what is represented by vertices in a particular protocol. This way, we could separate the global subset into into two subsets. So first one will be blockless DAGs, and the second one will be block DAGs, which was suggested by Quinn Wang in 2020. Example of blockless DAGs are Byteball and IOTA. In this type of DAGs, vertices are not blocks. So in example of IOTA, vertices of the graph are transactions that are referencing each other. In the initial paper, The Tangle, released by Sergey Popov, one new transaction is referencing to two previous transactions, confirming them at the same time. In Byteball, the vertices are special units of data referencing to each other. So the second type is block DAGs. In them, blocks are vertices and which are referencing the previously created blocks. Examples of the block DAGs are Hedera, Phantom, Waterfall, and multiple other projects. To be precise, blockchains are also a subset of a block DAGs. This presentation will be followed by the presentations of multiple protocols mentioned in this section, representing the different types of DAGs. To make this presentation complete, we will go through two more applications. Directed graph-based algorithms could be used to find an arbitrage opportunities. When we're having multiple currencies connected by exchange rates, we're having a complete graph, which is the graph whose vertices are connected to each other. So each vertex is connected to every other vertex in the graph. The algorithms used for this task allow for finding negative cycles in these complete or almost complete graphs. Such algorithms are frequently used Bellman-Ford and Floyd-Warshall. You can see the example of the negative cycle on the screen. So basically, the root starts from Ethereum, then it goes to DOGE, and then it goes to USDC, and then back to Ethereum, and the resulting outcome is actually bigger than the one which started. So this is how a negative cycle looks. Miner extracted value is a well-known attack when the miner is using its ability to include, exclude, or change the order of the transactions in the block. You can visit the site which is present on the slide to understand the scale of the profits extracted by attackers using this type of attack. Application of the elements of the transactional DAGs may make it much harder for miners to rearrange the order of the transactions. To simplify the explanation of this approach, utilization of DAG could be used to build a deterministic algorithm for ordering the transactions, which may make exclusion, inclusion, or change to the order of the transactions for miners almost impossible. So thank you so much for your attention. We appreciate your support of Ukraine. Please let me know if you have any questions. Otherwise, we will process to the next phase, which is the presentation of the DAG-based protocols.
Okay, thank you, Sergey. I'm going to launch the Hedera. Let me share my screen. Okay. All right, let me go share.
I'd like to talk to you about the 4 generations of DLTs, distributed ledger technologies. So of course, DLTs started with Bitcoin, just doing cryptocurrency. That's all it could do. That was the first generation. In the second generation, we were able to do more. We could store other kinds of information. So it could store who owns things like land or gold or art or whatever. We have things like NFTs, the ability to store who owns what in the ledger. So your distributed ledger technology actually becomes a ledger. But once people could do that, then we went to the third generation where they wanted to be able to buy and sell those things with each other. They wanted to be able to have smart contracts that had complex rules for what would happen and to be able to enable so that I could give you some cryptocurrency and you would give me a token representing a house, and it would be atomic, that you only get the money if I get the house, and I only get the house if you get the money, and you don't need a trusted third party. The ledger itself, in a decentralized way, replaces a trusted third party. But once we had the ability to do that, it was the time for the 4th generation. The 4th generation was markets. So if we can actually do buying and selling, now we need a way to match up buyers with sellers. And you have things like DEXs, and you need for this extreme speed, and you need great security, and you need fairness in the ordering if you're starting to put in bids and asks into these sorts of things or doing auctions. So those were the various generations. To be accepted by the world, and we're at the very early beginning of that, but to be accepted by the world, you need great performance, 10,000 per second. You need security, ABFT, which is the highest level of security. BFT means you're guaranteed to reach consensus and you're all going to agree. ABFT means it even works if your attacker can shut down some of the computers with, for example, a DDoS attack, distributed denial of service attack. If they can shut down one of the computers, it doesn't shut down your whole network. There are leader-based systems where you have that problem. If they shut down one computer, they shut down the whole network. until you switch to a new leader, but they could then shut down the new leader. They could play follow the leader and shut down the whole network. So for a BFT, the A means you can't do that. You also need stability where it's not going to be forking. You need good governance, not just a few shadowy figures that are maybe the top developers in back rooms deciding what's going to happen, but you actually have transparency where you can see the debates and see what the decisions are on what's going to happen with the network. And you need sustainability. Many people are concerned about the carbon footprint of some of these proof of work networks that just use more electricity than an entire country. You need something extremely efficient and green. So blockchain traditionally was a chain of blocks, and you had to take turns putting on the next one. You could use proof of work to decide who is the next leader. You could take turns being the leader. You could have proof of stake systems with the next leader, but these leader-based systems are not a good idea. With Hashgraph, we have a different approach where you don't have a leader. This is based on a DAG. I guess we're in the DAG section, but that's just one little piece of it. So to be doing the consensus model here, we are using a DAG in Hashgraph. It's a directed acyclic graph. It's a data structure. Lots of people do that. But in addition, it's BFT, which gives you math guarantees that you're going to reach the same consensus. And it's a BFT, which means that you have the A, meaning even if someone can DDoS and shut down some of these, do a distributed denial of service attack, you're not going to shut down the whole network that way. You'd have to shut down a third of the nodes to shut down the whole network. And it has fairness in the ordering, so you can trust it when you're using it for markets. It's not possible for one node to unfairly be delaying your transactions, and there's nothing you can do about it. And for these other ones where you take turns making the next block, that is a problem. So in a proof of work system, you have one blockchain, and sometimes a little side chain comes and they have to chop it off. It becomes stale. And you waste energy, you waste time. You might think that you were accepted, and then a little while later you realize your transaction wasn't. The Hashgraph is not like that. It's a DAG, and it just, everyone creates their blocks at the same time. Everyone does the transactions at the same time. And as a group, you then realize what the correct ordering should be. There's no leader picking the ordering. And so for a leader-based system, it's like a house of cards. If you can knock out just one card, you can knock down the entire structure. Same thing in a leader-based system. If you can shut down one, you shut down everybody. But in Hashgraph, you don't. It's just like having all the aces on the table. And if somebody takes away one card, that's unfortunate, but the others are still there. It's just fine. So this is the difference. So how does Hashgraph work? Well, one way that Hashgraph works is by having all the computers being submitted transactions to them. So Alice, Bob, and so on are the computers in the network. They have things being submitted to them. And if you submit your transaction to Alice, Alice can send it on for you by putting it inside of a message and just sending that to a random person, a random computer. And then the way gossip works is each of them sends it to a random computer who sends it to a random computer, and it just explodes exponentially fast. If you have one of the computers shut down, who cares? It still explodes exponentially fast. That's the beauty of gossip. Everybody gets it fast. But what if Bob and Carol each receive a transaction at the same time? Here's where systems start being different. In a leader-based system, you might have to decide who gets to send the next transaction. But in a system like Hashgraph, well, they just do it the most simple way. They send it at the same time. They don't take turns. They just send it. And so they send it, and they send it, and they send it, and soon everybody has it. And of course, we need to now put them in order because they all received them in a different order. But if you knew what time each person received it, you could then take all of those timestamps and you could sort all the red messages, all the blue messages, all the green messages, the times that they were received, and take the middle time, the median time of when everyone received a red one. That's circled there. That basically tells you when the red message first reached half the network. The blue one tells you when it reached half the network, and the green one tells you when it reached half the network. And so taking those circled ones, you can put them in order. And so you put them in order by their fair timestamps. That gives you a fair order. And the fair timestamps was the middle on that list, the median time when it reached everybody. Then the only question is, how do you find out when it reached everybody? Well, remember how I said Alice sent it to Dave? Look at this graph. This graph on the right shows you the circle at the bottom says that Alice started with it. And then she still has it on the next step, but Dave now has it too. This graph is drawing a picture of how it flows through the network. And once Alice and Dave have it, Each of them sends it to someone. So Alice sends it to Gina and Dave sends it to Bob. And you see that in the graph. The lines going up show you that Dave sent it to Bob and Alice sent it off to Gina. And so the graph can show you an entire history of exactly how information flowed through the network. And if that were the case, then all you would need is a timestamp by each circle in the graph, and you could just read off the graph what was the median time of when the red message reached everyone. And similarly, you have the green and the blue, and they reached everybody. And you could just read off the graph and know exactly what order they were in. And if all the computers had this graph, every computer would just know what order to put them in. And that is what we do. These messages don't just have transactions in them. Of course, they have a timestamp of when they're created. That's how we know when you receive things, is when you send out this message, this circle. But they also have the hash of the last two. And so for every one of these messages, you know the last message that was created by that node and the last message they received from someone else. And those two hashes then let you put together this entire picture. And so what this means is that when we're gossiping, when we're spreading out the information, we aren't just gossiping about the transactions, we're actually gossiping about the gossip itself. And so you get to see the history of how we all talk to each other. And that lets you see the times when people received messages, and that lets you tell the median time, and then you can put them in order by median time, and you have fair timestamps and fair orders, and we all have consensus. And we do this in a Byzantine way. I'm not going to talk about the details of it, but basically we all have a Byzantine agreement on which people participate and which people don't. That's what we end up agreeing on. Once we've agreed on that, you just take the median timestamps and you have fair timestamps, total consensus. So that's gossip about gossip with virtual voting. That Byzantine agreement requires zero information being transmitted back and forth. Just those two hashes are enough to get enough information to do the virtual voting. And so we do true BFT, ABFT virtual voting using gossip protocols that have been around for decades, but we do it virtually. And so it takes no more communication. This is as efficient as you could possibly be, and you still get all those guarantees about ABFT. So that's how Hashgraph works. We use that to build a ledger. We have it's a public ledger. The Hedera ledger is public. We have services like our token service, native tokens, and smart contracts. You can do smart contracts, and they can reach out and affect the native tokens. So you have the best of both worlds. You can do those native tokens, and you can be doing the smart contracts accessing them. But the native token transfers are 10,000 per second. And it costs you 1/10 of a cent to send a native token. This is extremely fast and cheap, still ABFT, and we have smart contracts, and the ordering of our transactions end up being fair. No one node can unfairly delay it. You get all of that. Lots of applications being built on it, lots of throughput. We're having, I think, almost more than anybody else in throughput per second right now. We are well governed with lots of these companies that you've heard of governing it, to jointly controlling it. We have the lowest energy usage. We are thousands of times better than the Ethereum after the merge, and we are millions of times better than Bitcoin in how much electricity we use. In fact, we're over 100 times better than just a Visa card. Using your Visa puts 10 times as much, 128 times as much carbon into the atmosphere as doing it on Hedera. Applications are all over the world. We are tokenizing real world assets. We're creating green bonds, not us. People are doing this on top of us. Supply chain applications, tracking them with NFTs, tokenizing service or ESG applications, even protecting civilians by getting them information in a war zone and recording things like the history, Holocaust survivors, recording their history. Just all sorts of applications across the board. And we don't even have time to even talk about all of them. Ashfall is a new AAA game about to come out using Hedera, built on Hedera, using Hedera for NFTs inside that game. So what you end up with is if you use a DAG like Hashgraph, it might or might, if you use a DAG, it might or may not be ABFT. But if it's Hashgraph, it's ABFT. You have incredible speed, 10,000 per second, actually transactions being processed 10,000 per second, not just gossiping them, reaching consensus in seconds, all the guarantees of ABFT, and then all these applications on top of it with great governance and with a huge developer community. I encourage you to talk to us and get more information about all of this. Thank you very much.
Okay. Now the next one, Aleph 0, is that correct, Sergey?
Yeah, it is correct if there are no questions to Lehman.
I can answer questions. I don't have my
Oh,
video.
sure.
For some
Yeah.
reason, I'm not
Hold
allowed
on,
to
let
turn on
me,
my video, but I can answer
no,
questions.
let me just promote you to co-host so you can answer questions.
Okay. If you can't do that, people can still ask me questions.
No, I could do that. No, just
Okay. Okay.
go ahead, Lehman. Any
Hello.
questions for Lehman?
Sure. I've already answered one in the chat.
Yeah. So why don't you look at the chat?
What's a smart contract layer? Solidity. You can take contracts directly from Ethereum and run them directly on Hedera without any changes. Of course, we have some addition things, some pre-compiles that allow you to do things like reach out to the native tokens and access them too. So it's all of normal Solidity, plus we have pre-compiles to do extra stuff. Thank you. Okay, well, if there's no other questions, get in touch with me if you ever have any questions.
Very good. Thank you, Lehman. I'm going to remove you from the spotlight, and then we'll go ahead with what did we say? This one is Aleph 0. We'll be launching Aleph 0.
And I would like to talk about BFT consensus protocols that are based on DAGs. This is joint work with Adam, Damian, and Michał, and we're all at the Aleph 0 Foundation. So what's consensus? In this talk, I would like to take a blockchain angle. So think of a system which keeps receiving transactions from users, and its goal is to publish a log of transactions that is linearly ordered. So the transactions will appear in this log one by one, and as more transactions are received by the systems, they are getting appended to the list. So the important properties of this system is that this list is append only. Okay, so there will be no rollbacks. Once something lands on this list, it will never be taken back. And there is no censorship in the system. Whenever a user sends a transaction, it will finally be appended to the log. And as you can imagine, such a log can be easily translated into a blockchain. So what kind of model are we talking about here? In this model, we have n nodes and a public key infrastructure between them. Each node knows the identities, being public keys, of the remaining nodes. When it comes to network, the most important point is the synchronicity model. The simplest model, synchronous one, assumes that whenever a message is sent, then it is received by the recipient after delta time, where delta is some fixed parameter. Then there is a asynchronous model, which says that whenever a message is sent, it will be eventually received, but there is no bound on how much time it takes. And finally, there is a partially synchronous model, which is somewhere in between, but I will not give you the formal definition. I think there is general consensus that for blockchain applications, these two latter definitions, partially synchronous and asynchronous, are good enough, while the first one is too weak. Regarding nodes, we will assume that there might be nodes that don't follow the protocol and actually can violate it arbitrarily. However, there will be at most n/3 of them. There are known impossibility results from the 80s that say that if you have more than n/3 such faulty nodes, then you cannot reach consensus. Here is a list of consensus protocols. Of course, it's not complete. It's just a biased selection. But the ones which I would like to single out here is, of course, PBFT, which was one very early consensus protocol, which inspired a lot of future work. For instance, Tendermint and Hotstuff, which now are pretty much state-of-the-art protocols for many blockchains. Then on the right-hand side, I compiled a list of what I consider as DAG-based protocols. The first of them is the work of Moser and Meyer-Smith from 1999, where they introduced a very interesting protocol and an idea called virtual voting. I will explain this idea at some later slide, but it is the very core idea in DAG-based protocols. Then 20 years later, many other protocols came, including Hashgraph, Aleph, Highway, Bullshark. These all protocols have their differences, many trade-offs between them, and I will not give you much details about that, but they are at the same time also kind of similar, and they share the same properties and the same core idea. Why do we like DAG BFT protocols? Well, I think the most important reason is simplicity. They're all very efficient, but I think the simplicity is even more important. So the simplicity comes from separating two aspects of the protocol, one being data dissemination and one being ordering data based on the messages that come from the network. So in many protocols that come from PBFT, these two aspects are kind of mixed and lead to complications in the protocol. There is also no such thing as a view change, which is a common thing for PBFT and many other protocols, which make the protocol kind of simple in the optimistic case, but then there is this pessimistic case which makes it terribly complicated. So for most DAG-based protocols, there is just one mode of operation, and it's simple. Awesome. So why don't we talk about IOTA or Avalanche? Well, they are also DAG-based protocols, but they are based on a different paradigm. So whereas in the protocols that I mentioned, there is a fixed committee, the Sybil protection mechanism in IOTA is kind of different. And also the goal of these protocols is not to achieve linear ordering of the DAG. So because of these differences, it's not easy to compare them fairly. So I will just talk about the protocols that I mentioned before, like Aleph, Bullshark, Highway, and so on. And as an example of them, I would like to talk about Aleph. And the idea is here that while I focus on one particular DAG-based protocol, I would like to talk about them as a whole. So there is a couple of ideas which are common and which you will be able to understand in this by listening to this talk. And then if you just pick up any paper, either Bullshark or Nalwar Tusk and so on, you will be able to understand the details by just reading a couple of more paragraphs. So let's dive into it. Assume there are 4 nodes in the protocol. One of them might be faulty. There will be rounds, and in each round, each node is responsible for producing 1 unit of data. The there is a rule that every unit, except for the unit in round 0, must have 2n/3 parents from the previous round. Okay, so it must reference 2/3 of the previous round units. Awesome. So what's the structure of the units? The unit consists of a round, a creator, the references to parents, and some transactions which we would like to order. There is also a signature. So now I would like to assume that once we create a unit, we use some reliable broadcast protocol to disseminate this unit to other nodes. What kind of property I'm interested in? I want that once an honest node receives a unit, it will then send the unit to all other honest nodes. They will receive it eventually. Okay, so this is the kind of reliability I would like to achieve. And how to achieve such a reliability is a different problem. It's a simple idea called reliable broadcast. Okay, so I'll not talk about it. I will just assume that this reliability is there. Once a unit is produced, it will be received by all other nodes. Awesome. So the DAG keeps growing, the units are getting disseminated, and essentially now the problem becomes, okay, so we have this partial ordering of units, so the relation here is the parent-child relation, and we would like to get one linear ordering out of all the units. Okay, given the ordering, we'll be able to order the transactions inside. How do we do that? Well, the problem is that at every point of time, the nodes might have a different local view of which units are there and which are not. Okay, so even though there is this guarantee that each unit will be eventually received by all other nodes, then because of network delays, each other node might have a different set of units available to it at a particular time. Right. So what we need is to reach consensus on which units are available and which are not. Okay. So what is this? It's just a binary decision, 0 or 1 on every unit, meaning 0, the unit is unavailable, or it maybe doesn't even exist. Maybe it is kind of available, but it didn't disseminate too quickly, and we just decided it's not available. But what's important is that if we have a 1, then this unit is available, meaning that all honest nodes either already have it or there is a guarantee that they will receive it at some point. Also, given this consensus on availability, it is already easy to get a linear ordering. Just go round by round and collect all units which are available and go to the next round and so on. So there is a very easy deterministic ordering which respects the partial order, which is based on these binary decisions. Awesome. So how do we perform the consensus on availability? This is where the idea of virtual voting comes. So given a unit U, the other units which are above it will vote on whether it is available or not, and the votes will be virtual, meaning they will follow directly from the structure of the DAG. So in this example, for round directly above the unit U, the voting rule says vote 1 if this is your parent and vote 0 if it is not. Then for round for the next rounds, the rule is different. The rule says if all your parents voted 1, then you vote 1. If all of them voted 0, then vote 0. If there is no unanimity, meaning there is zeros and ones among your parents, then use the default vote, which is assigned to this round. Okay, every round will be assigned some particular default vote. Great. So there is this very nice property of this voting scheme that once all the nodes, once all the units vote 1 or all the units vote 0 at a particular round, then this will continue forever, okay? Meaning that we have reached a consensus. The only question is when this happens. When will it happen that all the units in a particular round vote the same? And unfortunately, the answer is we cannot, if the network is asynchronous, we cannot really force it to happen. We cannot really force the consensus to happen. Why is that? Well, there is a general result called the FLP theorem, which says that in a asynchronous network it's actually impossible to do that. So how can we go around that? Well, let's look at the picture here. If you look at the votes between two rounds, then you can observe that there are two types of votes. Either these unanimous votes, which follow from all the parents voting the same value, or there are votes for the default vote. Okay, and it's important that the unanimous votes here, they will be always the same. Okay, because of the rules of the protocol. So now, if the default votes were kind of random, right, then we would have a 50-50 chance to hit consensus, because if this case we hit 1, then we are done. So this intuition kind of works if the network is partially synchronous and the adversary is not so powerful. The FLP theorem does not apply here, and we can just, well, use alternating 0-1 default votes, and this is a complete working protocol that achieves consensus. And if you're interested in a practical BFT protocol, then yeah, this is the end essentially. And the protocol ends, the protocol is fully described. You don't need to change anything, you don't need to add any other components. However, if you are interested in an asynchronous protocol, so this is more of a theoretical interest, but still, to go around the FLP theorem, you need randomness. So you need to use default votes, which are kind of unpredictable even to the adversary. And for that, we need an asynchronous randomness beacon. Okay, so how to do that? And this part of the talk is not directly related to BFT protocols. It's only how to get randomness for Aleph. So I will be quick and don't give you much details about that. And I encourage you to take a look at the paper if you are interested in that. Anyway, so how we normally generate randomness, it's we generate a BLS key, we share it among the n nodes, and then we get randomness by signing some nonces, okay? And the unpredictability comes from the fact that actually no one holds the secret key. It is shared, and only upon signing the signature which gives the randomness is then uncovered, okay? The problem is always with the dealer, so we need a trusted dealer to actually do the SHA-measure secret sharing, and we don't want trusted dealers for consensus protocols. So how can we circumvent that? Well, there is this idea which was around for quite a long time, which is to let every node act as a dealer. So if we do that, then there are lots of honest nodes, and if we then combine all the randomness sources, then get an unpredictable randomness source, because most of them are honest and we can trust them. Awesome. So by doing that, by forcing all nodes to kind of combine their randomness sources with at least n over 3 nodes, we have this guarantee that we will get unpredictable randomness sources from all nodes. Okay, so here is the situation. We have n unpredictable randomness sources, and we just would like to pick one of them to be the final randomness beacon. Yeah, the issue is we need consensus for them, so we need to find one which is available. And well, if we run consensus on availability on each of them, then we can just pick the one which is available and has the lowest index or something like that. Awesome. The problem here is that this looks kind of fishy because of the circularity. We need to get consensus, we need randomness, and to get randomness, we need consensus. Okay, so this is where I would like you to take a look at the paper, and because it's not possible to properly explain this in this short talk, and see how is it done. Awesome. So DAG BFT protocols, they are efficient, but most of all they are simple, and that makes them really easy to implement. And the programmers like modular structures, they like to test the code, and they don't like corner cases. That's something which DAG-based protocols actually give you. It's also possible to apply many different optimizations on top of the protocol I just described. And some of them are even implemented, some of them wait to be discovered. That's all for me. Thank you for listening.
Okay, so we'll feel free to ask questions. You can unmute yourself or type them in the chat box. And I'm going to start queuing up the next presentation, which will be IOTA. So let's have a
Brian, I think Damien is not here, so probably the questions should be asked if there are any. We can provide the information, so the contact information of Aleph Zero, so they can address the questions.
Okay. Do you have the contact information that you can drop in the box? Or do we want to leave that for later?
Yeah, sorry. I will post the information in the chat.
Okay, very good. Excuse me. All right, so now we're going to, we're going to launch IOTA. Let me share my screen.
Well, to all the DAG-based talks, I think us DAG folks need us. All right. First, I'd like to, welcome to my talk. First, I'd like to thank the organizers for inviting me here. It's been fun listening to all the other, to all the DAG-based talks. I think us DAG folks need to stick together in this world of blockchains. And if anyone's interested in exchanging ideas more, please write me and contact me. I'm very interested and open to collaborating and such. Anyhow, so first I wanted to start off with a history of IOTA to sort of explain a little bit where we are with our protocol, since it's a bit confusing. So you may have heard, I think, of most people are familiar with the first version of IOTA, which is the original version and using random blocks for consensus. The idea behind the original IOTA was that if you had a fork in the tangle, tangle is the name of our data structure that we use, that we have nodes do a random walk based on the weight, and then to decide where to attach to, and that decides the consensus. Okay, now well, this is old. It doesn't. There's some problems with it, and which is why we abandoned the idea and seeking of new things. In the meantime, what we are using is for current is a coordinator, and this is our Chrysalis upgrade that we had, and this is what we're currently doing. And we have we do a total order based on milestones. And so what we do then is, we just have a sausage here, and we have these milestones here, and we just basically, these things are all, first, and then these things are second, these things are third, and that's sort of the basis of our total ordering. And anything between the milestones, it doesn't matter how we order them, as long as the milestone is set in total ordering. All right, but is centralized, which is not good, and so is going to be the past. So, now the future is IOTA 2.0, which we've been working on forever, which is something different. And so I want to tell you exactly what that something different is. All right. So maybe first to talk about something different, what it means to be different. I sort of want to first touch base on traditional DAG-based DLTs. Is basically they usually have two layers. The first is the atomic broadcast, or sorry, reliable broadcast. And they have a reliable broadcast layer that basically what they do is they have a fixed number of nodes, 1 through n, and and these guys just each node issues blocks in a chain. So it's basically like we have a blockchain, several blockchains that are then woven together through these other blocks that people choose somewhere or another. And then we have this 2/3 confirmation rule, right? That basically, you have some rounds and things like that, but basically if enough rounds of 2/3 of the validators have seen you, then you've been seen by everybody and you're included. And then 2, there's some sort of total ordering mechanism based on that, right? Because if you have this sort of sausage type thing, there's bazillions of algorithms to totally order things, right? I know this is sort of a generalization thing, such, but yeah. So one of the key things, we always have this choice between safety versus liveness, and these guys, particularly with this 2/3 confirmation level here, always tend to choose for safety, right? If these validators go offline, then what do you do, right? Yeah. So IOTA 2.0, what does IOTA 2.0 try to do? So its design principle is kind of our twofold. First is this property dynamically available. And this dynamically available basically points, chooses liveness over safety. This is, crash fault tolerant, arbitrary crash fault tolerant. This is basically what Bitcoin, Cardano, which is the folks who coined this term dynamic availability, and Ethereum is also dynamically available, and basically adjusts to participation, basically. And what's nice is it gets rid of this this sort of fixed 1 through n validators. I mean, it's sort of not true, but it's sort of true in other senses, right? Because usually with these protocols, it's sort of very flexible who can enter and leave the validating set. Now, 2, second idea is we have parallel processing. I always misspell parallel. And so what is parallel processing? Well, what do we want to do? Basically, we want to validate / execute on arrival. Everything on arrival, right? And we want no total ordering, right? So we want to just see things, arrive, book them, and go on, right? Now, so both of these things do is give us two ideas. One is something that's very fast. It's a constant stream of updating perception, or constant updating perception, right? And this is sort of really the idea between Nakamoto consensus, right? And this is what's really kind of different than the traditional notion, right? Of these other sort of DAG-based DLTs, but they're really built off of like a pre-Nakamoto sort of classical consensus work that was done in the 90s, right? And here we're trying to more incorporate some of the more, these other ideas too. And the second is we want to focus on increased participation, right? Participation. So this 1 through n, like we would want this n to be basically, ideally, to be everyone in society, right? And that doesn't quite work with this 2/3 confirmation model, right? This is why we're sort of trying to think in a different paradigm. Yeah. So how do we do this? How does it work, I should say? Well, this algorithm that we have, our consensus algorithm we have is called Tangle. We call it Tangle 2.0. And there's a paper on this. You can find it if you want. Yeah, so basically how it works is that if you have, if you have the Genesis block and you have A and B, and then you have other blocks, build on top of this, and then new things coming on. Let's say that A and B conflict. All right. Well, so what do we do? So basically what we do is blocks have weight. Okay, and this weight is basically from DPoS, right? It's sort of people who issue blocks that have high weight are basically people who have lost stake delegated to them. All right, and then we count the weight approving a block. And then the heaviest wins. Right. Now I'm skipping sort of some steps in here. How do we do confirmation and such? But this is, I think, the basic idea, right? And notice that since we're just talking about heaviest and such, we're really kind of getting out of the ideas of like fundamentally 2/3 type paradigm, even though that does actually sort of come into our consensus mechanism if you read the paper. But this is very flexible. Okay. All right, great. But there's a problem. It's actually sort of there's two sort of unobvious things. One is there's this whole reliable broadcast layer that I'm skipping, how do you make sure that everyone has the same blocks? And this is not a trivial problem. This is also related to what happens if someone spams a whole bunch of conflicts, right? Because ideally what we actually want to do, right, is that we actually want to optimistically book everything as it arrives. We want to book A and we want to book B as it arrives, right? And then book everything that else too as they arrive. But you could if someone just spams a whole bunch of forks and things like that, what happens? Oh, okay, that's the whole reliable broadcast layer. It's another question. The second, which I am going to talk about, is tracking conflicts. Well, so because what if you have more complicated situations? Okay, so because this is here the situation here, we just have A and B conflicting, right? Well, I mean, what if we have more things conflicting? What do we do, right? So consider maybe this example here. So this is our tangle, right? And we have the genesis. And suppose we have a transaction, and we have A and B. For this transaction, these are all in blocks, and they're all referencing the genesis. And then we have a transaction here that is going there, and we have C and D here. That's going on to there. All right. And let's just assume that A and B and C and D are conflicting pairs. All right. So what we're going to do is well, the answer to this question is how we track now two conflicting conflicts. Well, do you like DAGs? We're gonna have more DAGs. So first is, well, we are using a UTXO DAG, right? That's sort of the essential for here. And basically then, okay, so we're gonna have transactions A, B, maybe a transaction here. And I guess my example is sort of similar. So we're not losing very much, right? But we've lost an arrow from here to there, okay? But if you have a lot more transactions, right, you can lose some arrows and things, and you kind of, actually the UTXO DAG should be very wide and not very deep, okay? Now, so that's one step. The next step that we have is what we call the conflict DAG, right? The conflict DAG should just consist of conflicts. And so that should be A, B, C, and D. Okay. I notice that we've reduced a lot of stuff. Now, most transactions, remember, in a normal case, the conflict DAG should be empty, right? So unless someone's trying to attack the network or there's a mistake or something like that. But yeah. So all right, cool. Now from the conflict DAG, we can create yet another DAG, a fourth DAG. We're going to call it a branch DAG. Okay. The branch DAG is a branch is a conflict-free downset. All right. Or another way of thinking of it is a valid opinion on the conflicts. Now here, well, what are the valid opinions? The one valid opinion is say, oh, I think A is right. Okay. Another valid opinion is B, right? Another valid opinion would be C and B. Now notice though, if you think C is good, then you also have to think B is good because C depends on B. And another one is D and B. Now, the last one I didn't mention is we call this the master branch, which is thinking nothing is good, right? And so what we have then is we have, this is naturally ordered by containment, okay? And we can go through here, we can sort of see this there's a branch, okay. And then we can go, this basically is a bunch of labels, all right, that we can go label everything with. And so we can label here, like these guys here are the master branch. These two guys here are the branch A, because this transaction depends on A, right? So this, if you think of this transaction, if you want to believe in this transaction, you have to believe in A. And similarly, this one is B, and this one is CB and DB respectively, all right? All right, and then we can go over here and do something similar, right? And start labeling, you know, we can label this graph as well. Okay. So basically, now what we actually do is we label every block with a branch immediately on arrival. So when we do the validation, we do the validation of the block. We look at the transaction. Okay, this is what the block is dependent on, and there's some algorithm for this, and this is actually a little bit more complicated, right? To prevent forking. But basically, the block contains information about who it's voting for, okay, about who, well, what branch it likes. This label is a vote. Okay. And what's interesting is that from thinking about this vote, that if you vote for a branch, what's great about this is this also technically means you vote for all the branches below you too. Okay. If you like CB, then you like B in the empty set too. Okay. And then heaviest branches between win. This is between conflicts, right? Because the master branch will always be the heaviest. All right. And so, so basically what this is sort of complicated a little bit, right? But it's a very, emergent structure. You always update it when, everything's booked on arrival and such, all right? And then you're able to easily, efficiently track all the conflicts, hundreds or thousands of conflicts. This is, important. So one of the reasons why I chose to talk about this, it's interesting, is that it can apply to all UTXO ledgers, right? And the reason why is because you can still do this, and so you can apply actually the same parallel processing on arrival on any sort of DLT. So this is something actually you could probably incorporate to your protocol, assuming you're using UTXO. Because basically what you're doing is you use consensus. You use your consensus algorithm to, instead of voting on conflicts or whatever, to decide on branches, right? So if you want to totally order all of your all your transactions or whatnot, then basically you can get a total ordering of your branches, and then that total ordering will also give you will also help you be able to decide between branches, and you can still do this parallel this parallel execution. Anyhow, thank you for my talk, attending my talk. My time is up, so I look forward to questions. Thank you.
Okay, any questions? People, you can unmute yourself or put questions in the chat for the speaker.
Well, I guess that means everyone understood everything. There aren't any questions.
Okay, if there's no questions, I'm going to start the next presentation on Phantom. Okay, sharing a screen.
Brian, I think the next one
Yes.
was supposed to be waterfall, but it's
Oh,
okay.
okay, sure. Yeah, no problem. Are you going to present that one?
Yeah, I will.
Okay, very good. Yeah, and then Phantom after that, after you? Or
Yeah,
when do we play Phantom?
yeah.
Okay, so back to you then.
Okay, one moment. I'm starting to share the screen. As you already know, my name is Sergey Gribniak, and I am here to present Waterfall, a scalable distributed ledger technology based on direct data cyclic graph. As you probably know, there is a growing demand for decentralized public networks in various areas of business, finance, and social life. Decentralized platforms allow for transparency, immutability, tamper-free data security, tolerance to to various types of attacks, and consistent logic. However, many enterprise class applications require high speeds, scalable ledgers, and perpetually low transaction fees. All changes that are not currently being met by most available decentralized network. To meet those challenges, we present Waterfall, a highly scalable smart contract platform for development of decentralized applications. So today's presentation will give us an overview of Waterfall protocol, the problem it addresses, its mechanisms of operation. We will review the DAG-based structure of Waterfall, its mechanisms and life cycle of a block in the block DAG network. We will conclude by describing the platform's current implementation and future work, followed by a brief Q&A session. So current blockchain solutions have three essential issues. So low performance and slow transaction speeds, high transaction fees, and the trade-off between scalability and decentralization. Waterfall provides a solution based on direct data cyclic graphs that overcomes these issues. The platform offers relatively fast finality, proof of stake consensus with the ability of recording multiple blocks simultaneously. So we're talking about finality in seconds. The entire system's performance is expanded as more blocks are published at the same slot, and the platform scales dynamically. While transaction fees are not growing significantly, are not expected to grow significantly even during the peak times. Waterfall overcomes the limitations of scalability while preserving decentralization. So Waterfall functional subsystem consists of nodes, validators, and time slots. So nodes are servers that are registered on the network and store all relevant records as ledgers. Validators whose accounts are credentialed to participate in proof of stake consensus algorithms. Time slots during which validators must create and distribute their blocks. Epochs is a combination of time slots where intermediate results are summarized and assigned to committees of validators for subsequent slots of the next epoch. Eras are a combination of the multiple epochs where coordinated changes of the network settings takes place and to improve scalability and increase productivity and economic efficiency. Shard networks accept transactions, combine them into the blocks, and make a reference DAG. The blockchain-based coordinating network is responsible for DAG linearization, block finalization, and the selection of validators. This network will soon also be updated to improve its performance, but currently we can reach pretty high scalability in the current implementation as well. There are multiple levels of waterfall, such it could be referenced partially as the similar approach of Ethereum 1.0, 2.0, 3.0. So we do have this long roadmap, but even if in current initial implementation, we can achieve a high level of scalability. Network nodes collaborate to create blocks of transactions lined up in a DAG, and the part of the DAG is sorted to finalize basically it is finalized to create a stream, which is a linear set of blocks. The remaining not yet ordered blocks form a spray. Within each time slot, a validator node has the validator node in a subset has the right to create a single block. The created blocks of transactions lined up in a DAG, part of which is topologically sorted and finalized into the stream. And the second part, consisting of not yet ordered blocks, is a spray. And basically, the weight of the spray is determined by the number of subnets currently working in a shard. When a new block is created, the block signer writes into it references to some blocks from the previous slot, so-called tips. So eventually, we in efficient environment, we are arriving to the situation where every block from the following slot is referencing to every block from the previous slot and confirming it. There could be this could be changed. This could be affected by the speed of the propagation of the blocks, and the system can adapt to this type of issues. Tip blocks. These are blocks which are not references by any other blocks before. So basically, when each slot forms a new set of blocks, these blocks are called tips. After next set of blocks is published, the following set of blocks is referencing to the previous one, and now the new set of blocks is called tips, and so on. Basically, the waterfall protocol is designed to accommodate a large number of validation, or basically of large number of validators, while at the same time remaining scalable. Basically, we are estimating for us to have like about thousands or tens of thousands, or potentially in our paper, we actually built an estimation of hundreds of thousands of validators, which will allow Waterfall to preserve the all three parameters of the known trilemma of scalability, security, and decentralization. So the waterfall, basically there are time control mechanisms which are dynamically, which adapt dynamically to the changes in the system parameters. This allows for self-sustainability of the network behavior throughout its entire life cycle. In the block DAG networks, nodes don't have time to exchange new blocks within the same time slot. So each block produced by an honest block producer is accompanied by links to all known tip blocks. However, dishonest nodes can produce blocks with any references, not just tip blocks. To get a reliable reflection of the speed of information dissemination, we have to isolate part of the DAG structure that was formed by honest links. Our model allows us to build speed estimates based on algorithms for solving maximum flow problems. This allows us to first optimize the speed of the slot time of the network, and second, exposes the bottlenecks in the propagation of blocks. So Waterfall's core tokenomics policy is integrated into the DAG-based system design. Nodes are financially incentivized to create additional communication channels in the information network. The aim is to optimize the ratio of the data replication with affordable transaction fees by incentivizing the positive behavior of each network participant and of the system as a whole. The DAG structure forces us to modify tokenomics mechanisms to empower the system with economic leverages for its sustainable development. We propose to set rewards for blocks in the DAG network based on the degree of confidence of topological structures. An incentivizing system provides protection from certain threats in the DAG structure. All honest nodes make common decisions based only on information recorded in the ledger without overloading the network. A validator's reward is based on the quality of the DAG block. So now let's talk about the life cycle of a block in the block DAG network. It begins in the shard. Basically, the life cycle begins in the sharding networks with the transaction pool. So a crypto wallet user generates a transaction to another user. The transaction is sent to a node of the block DAG network. The transaction is distributed to all nodes and added to the pools until the transaction hits the block. All nodes exchange pending transactions to be transferred to validators that select them for block inclusion. Whole transaction distribution among peer-to-peer nodes guarantees that all nodes receive the transaction and it will not have to request it. The next stage is block submission. A validator obtains the right to create a block in the shard network. A block that precedes all nodes in the block in the slot is called a spine block. The final stage is block propagation. After creating a block, the validator must distribute it in the network as quickly as possible. The block is referenced in the next slot for rapid finalization, and other validators check to confirm that the block was created correctly. At the beginning of each slot, the coordinating network receives a list of non-finalized spine blocks from the shard network. Members of the coordinating networks come to a consensus and share the result with the shard network nodes to finalize. The nodes perform sequential transactions and update the state of the system. At the beginning of each slot, the node receives a list of finalized spine blocks and arranges their history. Sequential transactions are performed and the state of the system is updated. The node that creates a block in a given slot is the hash of the last finalized block at the Merkle root stack. So at present, the main elements of our protocol have been implemented and low-end experiments are being conducted. So first of all, I would like to point to pay attention to the environment, to the test environment. So basically, we are using the lowest possible Amazon servers with 2 core CPU and 2 gigabytes of RAM. And to the reference, your cell phone has on average 4 to 8 cores CPU and 4 to 16 or sometimes even 3 gigabytes of RAM. So basically, these servers we are working with are weaker than the average smartphone. So second version of our testnet was released this spring, and with the average speed of 200 and my apologies, second version was released this winter, basically last winter. So an average speed of the transaction was a little more than 200 transactions per second. The modified version 3 was able already to process 3,600 transactions per second, and this is only with less than 20% of CPU usage. So we potentially could have launched faster, and we probably would be able to achieve higher scalability requirements, but that wasn't the need at that moment. So we use actual Ethereum virtual machine. So a big number of smart contracts can be literally copied and posted and still work on the waterfall testnet. The system security is supported by the same or very similar security assumptions that support the Ethereum network. So this is all I wanted to say about Waterfall Smart Contract Platform. Thank you so much again for your support of Ukraine. Today, Ukraine actually liberated Kherson, and I'm happy to address any questions if you have them. Thank you.
There's a question in the chat box. Does Waterfall require each node to run the same smart contract code logically simultaneously, like Ethereum? Can two smart contracts run together?
In current implementation, the answer is yes. In the following implementation, we are going to implement the subnets for the single shard and also a sharding. So basically, the subnets, I presented this concept this Monday. So basically, it states that the network can be separated by the same shard could be separated by a group of the smaller groups of strongly connected nodes, each of which are executing. In basically these nodes, they share the same transaction pool, and this transaction pool doesn't go to the rest of the subnets of this shard. And then these transactions can be later on put as basically they can update the state, and then the state is getting shared. So, but this will be probably in a couple of versions after this one. So it is a work in progress mode. But the initial paper is already published, and we will be updating it with future updates.
And there's one more question. You might want to read it in the chat. It's about sharding. Looks like what you've done is created sharded DAGs tied to a blockchain. Have you solved for atomic composability for transactions across multiple DAG shards in a single transaction? If so, how?
For you to have a picture of how Waterfall works currently, is you can think of Ethereum with enabled sharding, but in single shard we are not using linear blockchain, but we are using like a block DAG. We are also working and potentially will be implementing a DAG structure for coordinating network. So currently coordinating network works similarly to beacon chain in Ethereum and relay chain in Polkadot. So there are similarities with the approach, but we do believe that in the following updated versions, this will be updated. So it was built like this for initial launch.
And then the last question there, how are validators assigned across the shards to achieve the transaction volume at scale while not overpowering nodes?
We basically, we will publish the paper on this matter. So currently our research group is working on a separate paper which will be addressing these questions. We are currently working on the multiple approaches to this. And once our test results are conducted, there will be another paper describing this, basically covering this issue in particular.
Okay, thank you, Sergey. We're going to play the last Phantom recording. At the top of the hour, there's going to be another keynote in room E, Zoom room E, and then we'll reconvene for the DLT DAG tutorials in 1 hour from now. So let me just play the last presentation here. Make sure I've got it keyed up. Here it is.
To make an introduction to you about Phantom technologies and the progress we make so far. My talk today is Scalable Smart Contract Platform with Asynchronous BFT DAG. Here's an outline of my talk. I will cover a quick overview of blockchain and its application, Then I will introduce about Phantom and its current status of Phantom Opera Network. Then in the last part of my talk, I will give a brief overview of a few challenges that we investigating, such as virtual machine work and scaling methods such as sharding. Let's start with blockchains. People have studied blockchains for many years. They shift to use blockchain system to move from centralized system to permission networks to permissionless network. Decentralization gives many benefits, including no single point of failure, no single point of control, and its major advantage is the fault tolerance or percentile tolerance. There's a lot of application of blockchain, such as decentralized application in finance, entertainment, social networking, and many more. Blockchains have been used successfully in many places. However, there's still some limitation in existing blockchain technologies. For example, in proof of work, it has a long confirmation time and high power consumption, whereas existing proof of stake proposal do have some limitation related to security, scalability, and fairness. With Phantom, we like to solve the limitation, and in that part of my talk, let me introduce you Phantom and its Opera network. The core technology of Phantom is our legacy consensus algorithm. Legacy is permissionless, leaderless, asynchronous, percentile tolerance. Legacy is built on proof of stake and it's a DAG, a directed acyclic graph. So we use that to have a faster and more secure computation of consensus. Our latest white paper is Legacy Scalable Asynchronous BFT on dark streams, and it's available on archive. Everyone can download and take a look if interested in. Here's an overview architecture of Phantom Opera Network. There are several components. The Web3 API at the top, the EVM engine, state is stored in the blockchain, the legacy consensus engine, and the P2P component. Our legacy builds new DAG per epoch to save space and reduce the DAG info more effectively. About code structure, our code is structured as follows. GoPra and legacy space are the main repository of our implementation of the legacy consensus algorithm and Opera network. Opera SFC contains the implementation of SFC smart contract. Unlike other chains, we support on-chain governance on the Opera network, which is implemented in Phantom governed repository. Here's the pipeline from transaction submission to confirmation to execution. So basically, transactions are sent to transaction pool, and whereas they are sorted by gas price, and the legacy consensus engine is the core of the pipeline. It processes the local DAG on each node and computes the attributes event block and build new blocks. Once a new block is formed, it will be sent to the EVM processor for execution. In the next slide, let's start some basics about events and DAG. So what is DAG? In Phantom, a DAG is a weighted graph. Events are graph vertices, parent has are graph edges, and each vertex has a weight. So what exactly is stored in each event? So each event has an ID, the creator of who make the event, the person of the event, the subparent, the sequence number, the frame number, Lamport timestamp, and the current epoch. Legacy will take a DAG and compute the total ordering of the events. How Legacy can do that? Let's go to the next slide. Legacy takes as input a DAG stream of events, and then it computes the root, then it computes clusters. Next, it determines attributes. From cluster event, it takes the median timestamp of attributes from all nodes and assign this timestamp for the attributes. Once the new attribute is filed, I can distribute the new block. It will take the subgraph under the new attributes, and it only consider those events that aren't yet considered before. It then sort the event of the subgraph in the topological ordering. It will include transaction of these events into the new block. So for the whole process, we will have a total ordering of events and transactions. The whole process is deterministic and happens very quickly. Now in this slide, it shows how the main chain is formed. Starting from the DAG, it will compute attributes event block, and then it will compute a new block. The new block contains subtrap events under attributes sorted in topological order. The new block is then appended into the main chains. So, legacy consensus protocol is novel. As mentioned in the previous slide, the legacy is permissionless, leaderless, asynchronous, Byzantine tolerance. Legacy is built on proof of stake. And our legacy algorithm leverage local DAG on each node effectively to have a faster and more secure computation of the consensus. So for comparison, our legacy consensus algorithm is more deterministic and more secure than existing proof of stake protocols. Compared with the existing DAG-based approaches, legacy is also more deterministic and more secure. For readers, you can see our white paper for more details. Now, let's have a look at the current status of Phantom Opera Network. Phantom mainnet have launched in December of 2019. So within nearly 3 years, our network have grown steadily. The key features of Phantom Network is it is one of the fastest at the moment. The transaction fee is affordable, and one of the most secure platform at the moment. And on Opera Network, there's only one confirmation is required. So when a transaction is confirmed, it's final and it is immutable. Phantom mainnet currently have 64 validated nodes. It has confirmed more than 400 million transactions and around 50 million blocks. Minimum self-stack requirement is 500,000 phantoms to run a node. Now we give a brief introduction about some few challenges that we have working on to further scale the network. We are investigating several optimizations for more scalability of the Phantom network. In particular, we would like to increase the throughput. And at the moment, EVM execution is currently the bottleneck. We are working on several approaches, including virtual machine and other scaling methods for consensus. So for virtual machine, we've done a significant amount of work in research and development to improve storage and to optimize block processing time. As an example, we announced experiments with Apple, another key value store, and compared to the commonly used level DB, Apple is better solution for high performance IBM nodes. We continue to look at scaling methods such as sharding and a few others. So let's have a brief look about sharding approach in this talk. So sharding is a common term and well-studied research in database management. A shard is a subset of a large DB hosted on a separate trust server. When applied to blockchain, a blockchain network can be divided into distinct shards, and each shard stores a part of the blockchain data, and each process a unique set of transactions. Sharding have several benefits, and they also bring a few challenges. We are started sharding and a few other scaling methods in our next generation of lake acids. We will study lake acids with the currently DAG and DPLS to use shards. The advantage of using lake acid is its effectiveness handling of DAG for fast and secure sensors. Here the brief overview of some designs that we are currently studying. A committee is a set of validators that are responsible for the validation of shard blocks. Committees are randomly selected per epoch to avoid collusion. We like to maintain security of the main chain because it doesn't allow chain rearcs, as many other blockchain systems do, and we keep this target at deciding like I said next. The key advantage of like I said over the existing dark by approach is that like I said guarantees the total ordering of events and transaction. Sharding is one of the interesting research challenges, and Phantom would like to contribute some innovation in these research areas. In summary, what you've learned from this talk, like I said, is a permissionless, leaderless, and asynchronous Argentine tolerant consensus protocol, and like I said, it built on a proof of stake. Our algorithm leverage local DAG on each node effectively to have a faster and more secure computation consensus. Compared to existing proof of stake protocol as well as the existing DAG by approaches, like I said, is more deterministic and more secure. So what next? We currently working on a few interesting research challenges, and we're working to contribute this research in DLT in general, and we also want to further improve Phantom Open Mainnet in particular. So for more information, we will make them available in our new announcements and releases. On behalf of the Phantom team, I would like to thank to all of the people who support Phantom over the years, and thank you very much for your attention, and looking forward to see you.
Okay, very good. That's the end of the presentations for this tutorial session. We will reconvene at this same link in 45 minutes for part 2 of DLT on DAG. In about 15 minutes, a keynote begins. If you check your agenda, the keynote starts in 15 minutes on another link. Thank you all. Look forward to seeing you in 45 minutes. Go ahead. Yes, Sergey.
Brian, yes, that was actually the last presentation for this tutorial, so we don't have a part 2.
Okay.
Yeah, we covered everything. So there was an introduction, there was 5 protocols, and yeah, this was the tutorial.
Okay, so no part 2. Very good. All right. Well, very good. So the next keynote, I don't think the presenter, I don't see him in the participant window, so I don't, unless people have questions, or if you have questions, unfortunately the presenter is not here. So Sergey, were there other closing remarks you wanted to make about the DLT and DAG presentations?
Well, it was great to see you all here. Thank you so much for attending, and we do appreciate other projects which came to present and to cover this topic. And I believe those who missed the presentation, there will be a recording posted next week, right?
Yes, the recordings are. We have the recordings. They're going to be put up on IEEE.tv. It may take a week or 2 weeks. We have to kind of slice and dice all the recordings and package them nicely. But yes, all the recordings will be available for each of the speakers. If you weren't one of the speakers, you can purchase the recordings for a small fee from the conference proceedings. It's basically a virtual proceedings for this conference. So more information on that will be sent out to all of the attendees in the next probably 1 or 2 weeks.
Perfect. Thank you. This is all from my end. Thank you so much for having me.
Very good. Thank you, Sergey.
Yeah, have a great day.